physicists, we're going to look at gravitational fields. So on your doodle note, you can see that I've included a definition. A gravitational field is a region of space around an object in which there is a force of gravity from that object. So let's first go back to the force of gravity. If we think about an object located some distance above the Earth, let's say about there, the amount of gravity that's pulling it can be represented by a force vector. The farther out you go, for example, if you were over here, you wouldn't have as strong of a force vector. And the further out you go, that force vector gets even smaller. So these here in blue are force vectors. Now, when we introduce the idea of gravitational fields, you'll notice here that the strength of the force increases as you get closer to the Earth, but the direction was the same. So going to this definition, field lines show the direction of the force at a location in the field. Field lines are continuous, never cross, include an arrow showing the direction of an object in that field that it would be pulled. So I'll show you the difference here between the force vectors and the field lines. For field lines, they're continuous, so I'm just going to draw a bunch. I like to get the 8 major locations on the sphere. So if we were anywhere along this line, we'd be pulled in this direction. Same thing over here, we'd be pulled up. The arrows can be pointing right next to the object, but they don't have to. They never cross. So when we think about where would something over here be pulled, it'd be pulled always towards the center. So I'll add those force vectors. The field lines are in orange. So you consider the force vectors. If something was located here, it would be pulled in. And the field lines are just these continuous lines that show the direction of the force at that point. So you know, if you're here, you're getting pulled in this way. If you're here, you're getting pulled in this way. You can add more, but for the brevity of this note, I'll just keep it to 8. When we consider another object, let's say the moon, I've got it over here. The same idea holds. If we were some distance, let's say that same distance that we first looked at from Earth over here, the force vector would be smaller. And the further out you go, they still are quite small. We know that because the mass of the moon is quite a bit smaller than the mass of the Earth. But when you're drawing the field lines, you'll find if you were here, you'd be pulled in straight. If you were below, you'd be pulled in straight towards the center of the mass. So I'll do the same thing here, and I'll speed it up so you can see the 8 force vectors that I'll include here. You can obviously include some more, but you don't have to. All right, very good. So those force vectors, their length changes depending on the distance away from the object, but the field lines are these continuous lines that show the direction that the force would be pulling or pushing that object. Looking at these 2 astronomical objects, what you'll notice is that they each have their field lines. And the closer you are to Earth, the stronger the pull. We've seen that here with these force vectors around the moon. There is a point in between the Earth and the moon where the 2 forces are balanced. And this has a special name. It's called the Lagrange point. So what I'm going to do is simply create a line connecting the Earth and the moon. I'll just do it below, so I'm not going over those force vectors. And this line would actually extend into the centers, to their centers of mass. And this would be the capital R, the orbital radius of the moon. Obviously, the moon orbits around the Earth. So there is a point in between the two where the force of gravity from Earth is equal to the force of gravity from the moon. And at that point, you would have no field line because you would have an equal force pulling left as pulling right. This point has a special name, as I mentioned earlier. It's called L1, which is one of the 5 Lagrange points. And you'll see this pop up in your assignment. This Lagrange point is the point where those two forces are equal to one another, so there would be no field line at that particular point. But to the right, you would be pulled in towards the moon, and then to the left, you'd be pulled in towards the Earth. But at that particular point, there's no field line because those two forces are balanced. Moving along to satellites, I'm going to draw a small satellite here, orbiting around the Earth. And let's suppose it has a counterclockwise orbit. And let's call this R. What we've done so far in class was a lot of circular motion, and I mentioned that it would come back a lot in the rest of our course. So here again, we're going to have this idea coming back of circular motion. If we draw the FBD for this satellite that's in a circular orbit around the Earth, then we would know here that the force acting on it is just Fg. And from there, remember, we treat the centripetal force kind of like an F net. It's not something that we draw on the actual FBD. This Fc is equal to the force of gravity. So our mv squared over r is equal to, you'll recall this equation from way back. So here I'm going to use the capital M for the mass of the Earth, and you'll see that the mass of the satellite cancels out, and we can figure out the orbital speed just by rearranging this. This r and one of these r's will cancel out, so v squared is equal to g, the mass of the Earth, over the orbital radius, or a little bit nicer, g m over r, all square rooted. That is the orbital speed. You can use the same idea to calculate the orbital frequency or the orbital period, because we have some variations of this formula from the centripetal acceleration formula. What I'm going to do now is just kind of summarize the different variables that we'll be using throughout this unit. I've got them on the right here. You're going to notice that I use capital M's, lowercase m's, capital R's, lowercase r's to represent different things. So in general, this capital M is the mass of the larger object. This is going to be the object that is being orbited. So in the case of the Earth and the Moon, capital M would be the Earth, the object that's getting orbited. But in the case of the Earth and the Sun, this capital M will be the Sun's mass. And sometimes you'll see me using subscripts, but I want to keep these equations fluid so that you're not kind of stuck to one subscript. Likewise, lowercase m is the mass of the smaller object. So this is the one doing the orbiting. Capital R is for orbital radius. So the orbital radius is going to be the distance from the two objects' centers of mass. And it really is that radius from center to center, and then it goes through its orbit. Lowercase r is used for the radius of the object. So to make this clear, capital R would be the distance between the centers of the Earth and the Moon, or the Earth and the Sun, whatever's doing the orbiting. And then lowercase r would be like the radius of the Earth, or the radius of the planet in question. Capital T is the orbital period, so the amount of time to complete one orbit. And you'll recall the value g from grade 11 physics. It's 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared. That's the universal gravitational constant. So here are some equations that we can use, and I'll just briefly write down what they're used for. This is the universal force of gravity. So this one always applies. This, we would use it last year to calculate the acceleration due to gravity. We're going to call it now the gravitational field strength. Which for our purposes is really like the same thing as the acceleration due to gravity. This one we just tend to measure in newtons per kilogram as opposed to meters per second. They really do mean the same thing. It's just kind of viewing this topic through a different lens, not viewing it from a force of gravity kind of sense, but rather a gravitational fields lens. This is gravitational potential energy in general. So we have a more simplistic version that's used when we're dealing with a simple reference point like a roller coaster, and that one is just Eg is equal to mgh. So this one is a little bit more robust. You can use this in space for different objects and that sort of thing. This one here, we've seen this already. This is the orbital speed. So the speed that something orbits around another object. This one we're going to learn about soon. It's called Kepler's constant. I thought it'd be nice to have all your equations in one spot. And then finally, this last one here is for escape speed. And that is different from orbital speed. And we'll see that in a little bit. Any questions? Just let me know via email or on our